Welcome grade 12s to the next series of videos on chapter 14 and 15, Reversible Reactions and Chemical Equilibrium. This is lesson 1 and we are going to look at the definitions and some examples. What does reversible mean? It means that a chemical reaction can be reversed. A reaction is reversible if the products formed can change back into reactants. So the definition that we need to look at is, what is the forward reaction? The forward reaction is the reaction from the left to the right, where the reactants react to form products. And a reverse reaction is the reaction from the right to the left, where the products react to form the reactants again. Our first example is on page 175 of your textbook. We're looking at the reaction where hydrogen gas reacts with iodine gas to make hydrogen iodide gas. The ratio between the reagents are 1 to 1 to 2 moles. And the forward reaction is exothermic. I know it's exothermic because of the negative change in enthalpy. So energy is released. This means it's an exothermic reaction. The delta H is always for the forward reaction. So the forward reaction is the reaction where hydrogen and iodine changes into hydrogen iodide, and for that the change in enthalpy is negative 13 kilojoules per mole. The reverse reaction is the reaction where two hydrogen iodides decomposes to form hydrogen and iodine, and all these reagents are in the gaseous phase, so it's a homogeneous reaction mixture. For the reverse reaction, the change in enthalpy will be positive 13 kilojoules per mole. Right. Let's look at this reaction. If you take ammonia, which is actually a gas, and you mix it with hydrogen chloride, a gas, you'll get a solid forming ammonium chloride. Now this reaction where ammonia and hydrogen chloride combines to form ammonium chloride is also exothermic, meaning that delta H is negative. So the ammonia part plus the hydrogen chloride part making ammonium chloride, that reaction is exothermic, whereas if we take ammonium chloride, we'll have to put some fire below it to decompose into ammonia and hydrogen chloride. This is a decomposition reaction. And it is endothermic. And the first forward reaction is a synthesis reaction, and it is exothermic. So before we start with the the chapter 14, let's look at the rate of reaction graphs. Now, the rate graphs that we drew in the first chapter 13 will be slightly different to these rate graphs, because the amount of chemicals can never turn into a zero. So for the forward reaction, if we start off with a lot of reagents, the rate of the reaction will decrease with time, but it will never decrease to zero. So where we start off at T0, by T1, the forward reaction is still taking place. So the rate of the reaction with time, it starts fast, it slows down, and now the rate stays constant. Right, what will happen to the reverse reaction rate? If we go to the reverse reaction, we would most probably start with none of the products. So starting with no products, the rate of production of products is fast, and it slows down until it reaches a constant rate. So the rate stays constant, and it looks like this graph is a mirror image of the previous one. So the formation of the reagent slows down, and it started fast. Right. Next we will look at the combination of the two graphs on one set of axes. The important thing here is to know that the reactions will never stop occurring. While we have the reagents on the left-hand side and the reagents on the right-hand side of the double arrow, if it's a reversible reaction, the forward reaction will never stop, the reverse reaction will never stop. So the combination of the two graphs, that would represent the forward reaction, slowing, changing, and that would be the reverse reaction, changing. The place where the two graphs meet, the rate of the forward reaction equals the rate of the reverse reaction. Right, see you again in the second lesson.